Welcome to Daily AI and Machine Learning Lessons. I'm Blake, and today we're taking a deep dive into something absolutely fundamental if you want to understand how the increasingly smarter world around us actually works. The core approaches of machine learning. Specifically, we're going to unpack supervised and unsupervised learning. It's a crucial distinction, really, and it shapes everything from the apps on your phone to, well, the security of your finances.
And I'm Jude. That's right, these aren't just abstract concepts. They are the foundational methods that machine learning algorithms use every single day, to make our lives easier. Think about unlocking your smartphone with face recognition, maybe. Or those alerts you get for unusual credit card purchases. That's machine learning at work, and it's powered by these core approaches we're talking about.
Okay, so let's kick things off with supervised learning. When we say a model is trained using labeled data, what does that truly mean in practice? Like, what's actually doing the supervising there?
Yeah, that's a great starting point. When we talk about labeled data sets, imagine each piece of information arriving with its own verified answer key, basically. That label is precisely what provides the supervision. The algorithm makes a prediction, then it immediately checks it against the correct answer. It's kind of like a student who gets instant feedback on every single problem, adjusting its understanding until it consistently gets things right. This constant feedback loop is why supervised models can become, well, incredibly precise.
I see. So it's essentially learning from experience, but with very explicit, direct feedback. And when we think about applying this to the vast world of data, what are the big overarching types of problems where this answer key approach truly shines?
Right. Supervised learning primarily addresses two main types of problems: classification and regression. First up, we have classification. This is all about assigning data into predefined categories. Think of it as a super efficient digital sorter. If you want to teach a system to distinguish images of apples from oranges, for example, or maybe to automatically flag incoming emails as spam versus not spam, that's classification. The algorithm learns the boundaries, the lines between these categories. Common algorithms here include things like linear classifiers, which essentially draw a straight line to separate data points, support vector machines, which find the optimal boundary even in complex data sets, and then methods like random forest, which combine lots of tree models for better predictions.
Okay, so classification is about putting things into clear buckets, like spam or not spam, apple or orange. Got it. But what if we're not dealing with categories, but rather trying to predict a continuous value? Like, I don't know how much a house will sell for, or maybe product shipments next quarter. Is there a supervised approach for that?
Absolutely, yeah. That's exactly where regression comes in. While classification puts things into discrete boxes, regression is about predicting a numerical value. So instead of spam or not spam, you're asking how much or how many. Like you said, predicting sales revenue for the next quarter based on past data, marketing spend, seasonal trends, or forecasting housing prices based on square footage and location. That's regression. We use algorithms like linear regression for simpler relationships and more complex ones like polynomial regression when the relationship isn't just a straight line.
Okay, that makes sense. So far, we've talked about machine learning as like a student with an answer key, learning directly from these explicit examples. But what if you threw that student into a massive library? Books with no titles, no indexes, no categories, just pure information. Could they still find patterns, connections, meaning? That's the fascinating challenge that takes us to the other side of the coin. Unsupervised learning. How does this approach fundamentally differ?
Exactly that. Unsupervised learning kind of flips the script. These algorithms are designed to analyze and cluster unlabeled data sets. The critical difference is that there's no answer key. There's no human supervisor telling them what the right output should be. Instead, they work autonomously, discovering hidden patterns, structures, relationships within the data, all on their own. It's really about finding the inherent order in chaos, if you will.
So the machine essentially becomes its own detective, finding meaning without those explicit instructions. Interesting. What are the core tasks or problems that unsupervised learning models are best suited for then?
Well, there are a few main tasks here. The first one is clustering. This is a data mining technique used to group unlabeled data based on their inherent similarities or differences. Think of it like sorting a huge pile of diverse objects without any labels. The algorithm finds groups that naturally seem to belong together. K-means clustering is a classic example. It's incredibly useful for things like market segmentation, grouping customers with similar buying behaviors to tailor marketing, or even for image compression by grouping similar color pixels together.
Clustering for market segmentation, I can definitely see that being powerful. Any less obvious applications where grouping unlabeled data turned up surprising insights?
Oh, absolutely. That leads nicely into the next task, association. This method aims to find interesting relationships, dependencies, or correlation rules between variables in large data sets. It's the underlying magic behind those customers who bought this item also bought recommendations you see online all the time. A perfect real-world application is market basket analysis, where you discover what items are frequently purchased together, like finding that people who buy bread often also buy milk. It helps retailers optimize store layouts or maybe bundle promotions. It's all about uncovering those if-then relationships. It can lead to some surprising things. I remember an analysis where people buying diapers late at night were also often buying beer, not something you'd intuitively connect without this kind of analysis.
Huh, okay. Diapers and beer. That's unexpected. And finally, you mentioned dimensionality reduction. That sounds like we're trying to squish information down. My first thought is, why would we want to get rid of data? Doesn't that risk losing important stuff?
That's a really good question. And it's less about getting rid of data, maybe, and more about finding the most efficient way to represent it. Dimensionality reduction is a technique used when the number of features or dimensions in a dataset is just too high. Imagine trying to visualize data with thousands of features. It's impossible for us humans. Its purpose is to reduce the number of data inputs to something more manageable while preserving the most crucial information. So data integrity is key. It simplifies the problem for the algorithm, makes it easier to process. It's often used in data pre-processing, cleaning and preparing data. For instance, autoencoders can use it to effectively remove noise from visual data, which can significantly improve picture quality or just make the data easier for other models to handle later.
Okay, so we've explored both supervised and unsupervised learning now. For you, our listener, what's the absolute core distinction? If you had to boil it down to one key takeaway, what would it be?
The main distinction, without a doubt, comes down to the data itself. Supervised learning fundamentally relies on labeled input and output data. The algorithm learns from explicit examples of correct answers. It's like that student with the perfect answer key we talk about. It makes a prediction, compares to the correct answer, and then precisely adjusts its internal workings to get better. This typically leads to highly accurate models, but, and this is a big but, it demands significant upfront human effort to label all that training data. Think about training a model to predict commute times. You first have to painstakingly label data to tell it that, say, heavy rain adds 20 minutes. That takes time and expertise.
Right, so the human is explicitly teaching the machine specific rules or outcomes based on labeled examples.
Precisely. Unsupervised models, on the other hand, dive into unlabeled data. They work autonomously to discover the inherent structure within it. They don't have an answer key. They find patterns independently, but here's the kicker. They still require human insight, human judgment, to validate whether those discovered patterns are actually meaningful or useful. For instance, an unsupervised model might group customers who buy baby clothes, diapers, and applesauce. The model found the pattern, sure, but a human analyst still needs to step in and say, okay, does this grouping make sense for a recommendation engine, or is it just a statistical fluke?
That's a crucial point about human validation, even in unsupervised models. It's not entirely hands-off then. Beyond the labeled data piece, what are some of the other critical differences that really distinguish these two powerful methods, maybe in terms of what they're trying to achieve?
Sure. Well, let's start with their goals. Supervised learning aims to predict specific outcomes for new data, where you generally know the kind of results you expect. You're building a predictive tool, essentially. Unsupervised learning, however, is more about gaining insights from large volumes of new, uncharted data. Often the machine itself determines what's interesting or what patterns emerge, patterns you might never have even thought to look for. It's more exploratory.
And what about their common applications? Where do we typically see each one being used in the real world?
Right, for applications, supervised learning models are the real workhorses for tasks like spam detection, sentiment analysis, figuring out if text is positive or negative, weather forecasting, dynamic pricing predictions, things like that. Unsupervised learning, by contrast, excels at things like anomaly detection, flagging unusual financial transactions. For example, building those recommendation engines we mentioned, segmenting customers to create really targeted personas, and even complex areas like medical imaging analysis, finding subtle patterns in scans.
Okay. And computationally, do they require different levels of processing power?
Oh, definitely. Supervised learning is generally considered simpler, computationally speaking. You can often implement it using standard tools like R or Python. Unsupervised learning, though, that's significantly more complex. It often requires more powerful tools because it's dealing with vast amounts of unclassified data. And it needs quite large training sets to produce really meaningful, robust outcomes. It's It can be a heavy lift for the machines.
Makes sense. And finally, no approach is perfect, right? What are the inherent drawbacks of each? What limitations should our listeners keep in mind?
Absolutely, good question. A major bottleneck for supervised learning is that training can be incredibly time-consuming and expensive. That whole labeling process we discussed, it often requires specialized human expertise. Imagine hiring a team of doctors just to label millions of medical images. It's not just time, it's a huge financial and logistical hurdle. That often limits where supervised learning can be practically applied, despite its accuracy. For unsupervised methods, the main drawback is the risk of getting wildly inaccurate or just irrelevant results if there isn't that human intervention to validate the patterns. They can find patterns, yes, but those patterns might be statistically sound but practically meaningless without a human in the loop checking things over.
So for you, our listener, the crucial question becomes, how do you navigate this landscape? How do you choose the best approach for a given situation?
Yeah, that decision really hinges on a few key factors that anyone building or using these systems needs to assess carefully. First, you absolutely have to evaluate your input data. Is it labeled already? Is it completely unlabeled? And critically, do you have experts available who could potentially support additional labeling if needed? That's a big one. Second, you need to define your goals very clearly. Are you trying to solve a recurring, well-defined problem where you kind of expect certain outcomes? Or does the algorithm need to discover totally new, unpredictable patterns you haven't even thought of yet? And finally, you must review your options for algorithms. Think about whether the algorithms you're considering are compatible with the dimensionality, the number of features of your data, and can they efficiently handle your specific data volume and structure.
Right. So it sounds like a real trade-off then. Supervised learning gives you high accuracy, you can trust the results more, but it struggles with massive complex data sets, especially with that labeling cost and effort. Whereas unsupervised learning can chew through large volumes of data in real time, find novel things, but well, there's less transparency in how it groups things and a higher risk of inaccuracy or just finding junk without careful validation. This kind of brings us to a really interesting middle ground, doesn't it? Is there something in between?
It absolutely does, and yes, there is. When you find yourself in a scenario where neither purely supervised nor purely unsupervised learning seems like a perfect fit, there's what we often call a happy medium, semi-supervised learning. This approach strategically uses a training data set that contains both labeled and unlabeled data. It's particularly useful when it's really difficult or super expensive to extract the relevant features from raw data, or simply when you have a very high volume of data, making full labeling just impractical.
And we see really compelling real-world uses for this, especially in fields where maybe that expert labeling is absolutely crucial, but just can't get enough of it, right?
Precisely. Semi-supervised learning is almost tailor-made for areas like medical imaging, for instance. Imagine a scenario where a highly specialized radiologist can painstakingly label just a small subset of CT scans identifying tumors or specific diseases. That relatively small amount of highly accurate labeled data, when combined with a much larger pool of readily available unlabeled scans, can significantly boost the machine's overall accuracy in predicting which patients might need closer attention. It effectively leverages the best of both worlds. You get the precision from the labeled data you do have, and the ability to scale using all the unlabeled data that's available.
Considering the nuances we've discussed today about how AI learns from both labeled and unlabeled information, what do you think this implies for the types of problems we'll be able to solve in the future? Especially as the sheer volume and complexity of data just keeps growing, almost exponentially. It's definitely something to ponder. That's all for now, folks. Please like, share, and subscribe to help fund this channel.